Dear students, in the morning I have given you one part of the characterization theorem of bipartite graphs, and in this video we will not be completing the proof, but we will have a major part will be dealt in this video. We have already seen if G is bipartite, every cycle in G is even. No odd cycles will be present there. Now, before proving the converse, I require two definitions. One is section of a path. What we mean by section of a path? If you are given a UV path P by a WZ section of P, that's how it's mentioned, we mean a path Q. Actually, it's a subpath of P such that the initial vertex W and all other vertices up to the final vertex Z of Q follow the same sequence as that in P, and there is a thing which you have, and all those vertices from W to Z in that order are the vertices of P. So this is what I mean. Suppose you have a path P like this. Suppose this is U, this is V. Let me choose anybody. It may start from U also. So let me choose this. Then I have to definitely choose this. Then if I call this as W, this as Z, then it's over. Suppose I choose this one. So this piece is a WZ section of the UV path. So that means a part of the given path. That's section. That's what we mean by section of a path. Then inverse is already we have seen in what is meant by inverse. It means given a path P starting with a U1 and ending at UN, there are n-1 edges actually in a graph. Its inverse is nothing but traversing back. Inverse is again a path starting from UN and ending at U1. Previously it was starting from U1 and ending at UN. Now inverse means going backwards. That is inverse. So inverse of path is a path itself. Okay. Now we'll go for proving the converse of characterization of bipartite graphs. Here is the converse. Let G be a graph which has no odd cycles. So what we have to assume, you are given a graph G which has no odd cycles. So you have to prove that G will be definitely a bipartite graph. So we'll deal with two cases. Case 1, we assume for the time being that G is connected. In the case when G is not connected, we will have it as case 2. Okay. So what we have so far, you are given a graph G which is connected and has no odd cycles. What we have to prove? We have to prove that G is bipartite. To prove that G is bipartite, choose a vertex U belongs to V of G and define X and Y. These will become partite sets for V, such that X is all vertices of graph G, such that distance from this selected U, already we have selected U, distance from that selected U to this V is even. So length of distance means actually length of the shortest path. So length of the shortest path from U to V is E1. Such vertices are kept in V. Let me give an example. For example, if I have this graph, let me have this one. Then, yes, suppose this is U. Then we see, what is distance from here to this vertex? If I call it as say U1, distance is 1. Now from this U2, this is the distance, actually shortest distance. Therefore, U2 will be in X. So distance 0, 2, 4 are all in X, and distance vertices which are not in X are kept in Y. So Y is complement of X. Clearly, U belongs to X because D of UU is equal to 0. 0 is an even number. Therefore, U is a member of X. Now we have to show that every edge of G has one end vertex in X and the other in Y. In other words, there are no edges with both end vertices belong to X or both end vertices belongs to Y. That means the edges of the graph G has one end vertex in X and the other end vertex in Y. In X itself, if you choose to, this is not possible. Here also, if you choose two vertices in Y, that kind of edge is not possible. Edge occurs only across X and Y. That's we have to prove. So for that, what we do is, proof is very lengthy, you have to be very careful. So what we have so far we have U, which is a fixed vertex. With respect to U, we have constructed X and Y. Now we select two vertices in X, and we'll prove that there is no edge VW, edge connecting V and W. Before proving that, it takes time. So anyhow, we have chosen two vertices in X. So as V belongs to X, this distance must be E1. And W belongs to X means this distance Q must be E1. So P and Q are E1. So let capital P be the UV shortest path of length small p, and capital Q be the UW shortest path of length Q. So P and Q, capital P and capital Q may have common vertices for path P and Q. Let W1, so this choice of W1 must be very specifically understood. Let W1 be the last common vertex to both P and Q. There may be common vertices to, I'll draw a figure and then it will be clear. Before that, let W1 be the last common vertex to P and Q, such that W1V section and W1W section of Q have no point in common. So this is the figure I mentioned. The green colored vertices are path P, and the Z colored vertices are path Q. Okay, path Q means I was to throw it by, okay, this is, let me color it by black. Okay. This is the edge starting from U, then goes like this. It's reached here. This is common vertex. So this goes here, then it goes, and finally it reaches here to V. So UV path, from U to V, that is P. From U, starting with U itself, but ending at W, that is marked as Z. So let me mark the other path by another yellow. Okay, this is U, W is path. See, this is a common point. This point is common to both. This is also common. This is a common path, common vertex. So this is the path. So I'm moving from U to W. Okay. So this is what is mentioned here. This is a common point. This is a common point. U is also a common point. And W1B is the last common point, after which there is no common. So this is W1B section and this is W1W section. W1B section of P and W1W section of Q. So this is, after this, this video will be enough, and a few more sentences are to be added to complete the proof that we will have in the next video.